All right, we are going to start out with our limits, and do remember the first attempt that you do with all limits would be a substitution. So let's see what we get when we substitute for number 1. We have times 3 squared plus 3 times 3. And this looks like it's going to work out nice and neat here. We're going to have 6 plus 9. So our limit value is 15. Okay, so moving on to number 2, we do need to substitute first. Always make that substitution. So that's going to give me 0 over 0. So when this happens, that means that we probably have a hole in the graph somewhere, and so we need to factor and cancel or do some kind of rationalizing, something of that nature. So we're going to pull this function down here, and we're going to factor t squared minus 16, so t minus 4 times t plus 4. And remember, when these things are canceling, you are dividing, so there's 1 left after they're canceled. So now let's go back and reevaluate our limit as t approaches 4 of 1 over t plus 4, and notice that we have a limit value of 1/8. Moving on to number 3. Again, we do need to try substitution if we can. It does look like we can factor the problem, but again, we don't know if that's necessary yet. So let's do our substitution. So I'm going to have 9 plus 15 plus 6. And that's going to be over, so that is going to be over 0. And so notice here with this problem, it looks like we have 30 over 0. So this fits into number over 0, so we need to remember that's talking about a vertical asymptote. Oh, I don't need to abbreviate that. That says ASY, A-S-Y-M-P-T-O-T-E. Sorry, folks. So that's a vertical asymptote. So that means that we need to approach on each side of -3. So it might be easier to factor and try to cancel. Let's try that and see, just for grins. So x squared, that's going to be x and x. And it looks like we're going to have a -3 and a -2. And in the denominator, we do have a 2 we can factor out. But notice nothing is canceling here. So we need to look at our limit from the left and from the right. So I need to look at, my pen didn't work, the limit as x approaches -3 from the left of this function. And so I'm going to go ahead and recopy that. And again, you're doing this because of the vertical asymptote. You're approaching that, and you need to know, well, is your function heading toward positive or negative infinity? So here to the left, I would choose maybe something, let's see, negative, I don't know, 3.1 if you wish. So if we choose something a little bit to the left, then plug in. Notice we were going to get, let's see, negative 3.1. So we're going to have a negative times a negative. And then that's going to be over a negative. So that's going to tend toward negative infinity. So let's come back and talk about from the right side. And it looks like I might have to do some erasing here. So from the right side, when we set this up, then we're going to have that same situation again. I need to put back in that 0. So now let's look at the limit as x approaches -3 from the right of all this stuff. And notice that what we're going to get when we plug in, let's say -2.9, we could do that and plug in. So I'm going to get a negative times a negative over a positive. So that's going to tend toward positive infinity. So the limit from the right is positive infinity, and the limit from the left is negative infinity. So this limit does not exist. Okay, and again, the only reason we did that is because we were approaching a vertical asymptote. Right, now for this one, we have to remember our trig values. We are substituting in pi for theta. This 2, that means that entire quantity squared. and 3 times cosine of pi. So that's just going to be 0 minus 3 times negative 1. So that's going to give us a positive 3. Okay, moving on to number 5, we're going to substitute in, and we're going to get 0 over 0, which again is not a vertical asymptote. That means that we have some kind of hole in the graph, and we need to factor this, and we're going to use that formula that we had above. And when we factor this, we're going to have x squared, and then we're going to have plus 2x plus 4, and that's all over x minus 2. And again, we're going to have those x minus 2's to cancel. And so now we go back and we reapply our limit as x approaches 2. And then here we're approaching that with this function here. And when we substitute in, hopefully we end up with 12. Okay, and then number 6, again, same thing. We are substituting in pi over 3. So we're going to look at tangent of pi over 3 over pi over 3 squared. Now, a lot of people freaked out when they saw this. Once you figure out what tangent of pi over 3 is, which is just going to be root 3, you're welcome to leave the denominator just like this. It is okay. You don't have to go ahead and multiply that out any further. Okay, for number 7, when we work this one out, of course, again, we still need to substitute in our 0 to see what happens. And we do end up with 0 over 0. So again, that's a hole in the graph. We need to do some kind of factoring. But with this, that's a weird thing to try to factor. So here we're going to include factor or rationalize. And so we're going to go through and rationalize. All right, so we're going to just pull this down to the side, and I'm going to have the square root of x plus 5 minus square root of 5 over x, and then I'm going to multiply the top and bottom by the conjugate, which is going to be x plus 5 plus root 5 over the square root of x plus 5 plus 5. And again, please don't multiply all this out. It is not necessary. You just need to multiply across the top, and you're only going to multiply the first 2 terms. So I'm going to multiply this to this, and that's going to give us x plus 5. And then I'm going to multiply here to here, so that's going to give me minus 5. And then on the denominator, we're just going to bring every single part of this over. We're not going to multiply through with it because something is going to cancel. And notice here, these 5's will cancel, and also the x's will. But I'm going to do that in another step so we can see clearly that those x's will cancel. So I have the square root of x plus 5 here, plus square root of 5. All right, and now those will cancel, and remember that's a 1 left up there. Now we can reapply the limit. Now we can go through, and we're going to have the limit as x approaches 0 of 1 over the square root of x plus 5 plus root 5. And now our limit as x approaches 0, we're going to make that substitution. And we have the square root of 5 plus the square root of 5. And you're welcome to stop there. You don't have to continue with that. All right, number 8. So again, we're going to have to do some substitution to see what happens. And then here, let's see, if we substitute in 0, I have 1/3 minus 1/3 all over 0. And again, that results into 0 over 0. So that means that we're going to have to do some kind of factoring or rationalizing, which in this case, what we're going to have to do is simplify our fractions. We're going to take this whole part here, and we're going to simplify it. So back in Algebra 2, y'all were told whenever you add fractions, let's say you have a over b plus c over d, you're going to cross multiply these, so you're going to have AD plus BC, and it's all over the product of the denominators, BD. So that's what we're going to do here with this. So whenever I start multiplying this, I'm going to multiply 1 to 3, keep the subtraction sign, and then 3 plus x multiplied to 1. So I'm going to move that down here. And then that is all over the product of the denominators, which is 3 times 3 plus x. Now we don't need to forget, that's all just the numerator, so every bit of that is over x, which looks very intimidating. So let's see if we can't clear some of this up. In the numerator, we're going to have 3 minus x over, and I am not going to multiply this out, and I encourage you to do the same. Okay, and then in the top here, those 3's are going to cancel, so I'm left with negative x over 3 times 3 plus x, and that is all over x. And this is where we're going to have to go all the way back to our dividing fractions, and we're going to look at keep, change, flip. This is our top part. That is the part that we keep. So I'm going to have negative x over 3 times 3 plus x. And then we're going to change our division to multiplication, and we're going to flip that second number. That's our dividing fractions, because here's our two fractions, and we can think of that x over 1 if we need to. So we did our keep, change, flip, and now those x's will cancel. So I have negative 1 over 3 times 3 plus x. And now we're ready to go back, and let's reevaluate this limit as x approaches 0 of negative 1 over 3 times 3 plus x. And that ends up being negative 1 over 9. Okay, and there's another problem very similar to this that we will go through. Number 9, again, this is a good review of our natural log properties. We're going to substitute e into the problem. So I'm going to have 3e over the natural log of e. And earlier, somewhere in your notes, you were told that the natural log of e is 1. So this final limit is just 3 times e. All right, number 10. A big hint that we're going to have to do some kind of substitution is the fact that the limit as x approaches 2 is from the right. Let's go ahead though and make a substitution just to see what's going to happen. And if we do, we're going to have 3 times 4 plus 14 plus 2, and that's going to be all over 0. So obviously we're getting some kind of number here. Let's see, 12. So we're getting 28, maybe I did my math right, over 0. So if we have 28 over 0, that's number over 0, which means that we're going to have either a positive or a negative answer, or positive, negative, infinity, or does not exist. Well, never mind, not does not exist, it's one-sided. But the big thing here, that 28 over 0, that's implying that we have a vertical asymptote. And we need to get in the habit, every time we see number over 0, that's a vertical asymptote. And that means that my answer will tend toward positive or negative infinity if it's one-sided. So let's go ahead and do our factoring here. And I'm still going to move this limit down as x approaches 2 from the right. And when we factor this, we have 3x and x. And it looks like we're going to have plus 2 plus 1. And then in the bottom, now some folks are all excited because this does factor and cancel. But again, let's go ahead and cancel, but let's reevaluate that limit. And when we do, notice we're still getting 6, 7 over 0. So we're still getting a vertical asymptote. So we're going to look at a value just to the right of 2. So let's let x be maybe 2.1. So we're going to substitute in. So I'm going to have 3 times 2.1 plus 1 over 2.1 minus 2. And again, we're just interested in whether or not we get a positive or a negative. Notice we are getting positive over positive, so this is tending toward positive infinity. We don't have to approach the other side simply because we are looking at a one-sided limit. All right, and I think this next example, 11, is like the previous one. we do need to make our substitution to see what's going on with it. And when we do, we're going to get 1/3 minus 1/3 over 3 minus 3. So I'm going to get 0 over 0. So again, that means we're going to have to do some kind of factoring, some kind of algebra magic would be a better way of putting that. We're just going to do some Harry Potterism right here. So we're going to have to find a least common denominator. So again, I'm going to have 1 over x minus 1 over 3 over x minus 3. So what I'm going to do with that is I'm going to do some crisscross multiplying. Again, we're still going to be x minus 3 on bottom. And so I'm going to have 3 minus, because that's the sign between them, x over this product, x times 3, or 3x. Now I'm ready to go ahead and do my keep, change, flip. Here's my top fraction. Here's my bottom fraction. So I'm going to keep the top. I'm going to change to multiplication, and I'm going to flip the bottom. Okay, now these x values should cancel. They are opposites, and when you cancel opposites, you have a -1 left. So I end up with -1 over 3x. Now we're ready to reapply our limit. So we're going to go back and look at the limit as x approaches 3 of -1 over 3x. And again, I get -1/9. So there's another example of going through and having to find a common denominator. Number 12 is a great example of what you're going to have to do to factor. Now the first thing, again, let's go ahead and plug in our 3/2. So I have 8 times, let's see, 3/2 cubed. 3 cubed is 27 and 2 cubed is 8. Minus 27 all over, and again 2 times 3/2 minus 3. And after we do some number crunching, we will get 0 over 0. Now we need to factor this, and that's going to be the difference of cubes. And so we're going to just use our formula here and ask ourselves what's being cubed minus what else was being cubed. And then the rest of it we're filling into our formula. So all of this stuff is coming from that formula. And again, we see that the 2x minus 3's should cancel. And now I can go back and reapply this limit as x approaches 3/2 of 4x squared plus 6x plus 9. And when I make that substitution, let's see, we're going to have 4 times 9 over 4 plus 6 times 3/2 plus 9. And do remember, this would be on the non-calculator portion. So that's going to give me 9 plus, oh, well that worked out nice, 9 plus 9. So my answer is 27. All right, moving on to the next problem. Again, substituting in, and some folks, they're, again, a little bit rusty here. If we plug in, we're going to have cotangent of pi. So this is one-sided, so we can't write simply does not exist. We're going to have to talk about either positive or negative infinity. So let's see, cotangent of pi, a lot of times we don't remember right off our tops of our head. So let's go through and change cotangent. That was really cosine of pi over sine of pi. And then here, cosine of pi is -1, and sine of pi is 0. So we have a number over 0, which is going to tell me this is a vertical asymptote. So that means I either have positive or negative infinity. And most people don't remember what the graph of cotangent looks like. It's kind of strange. It does something like this. And it does repeat itself over and over and over. And that's why we have this asymptote here. So instead of going through and trying to remember what the graph looks like, think about your quadrants and how they're ordered, because we're talking about pi. And if we ordered these on a number line, wouldn't we, let's see, we would start out, we would have 0, and y'all did pi over 2, and you did pi, and then next was 3 pi over 2, and then finally 2 pi. That was the order of it on the number line. And so if you need a little bit to the right of pi, then that means you're looking somewhere between pi and 3 pi over 2. Well, here's 3 pi over 2. So notice that you are in the third quadrant, and we know cotangent and tangent in the third quadrant, they're positive. So this is tending toward positive infinity. All right, so 14, again, some more trig. We are substituting in our 0, so I have cosine of 0 plus sine of 0. So that's going to tell me that we have cosine of really just 0, which is going to be positive 1. All right, moving on to the next. With our piecewise functions, with our limits, and again, notice this limit's not talking about just one side of it. So you've got to approach both, and that's what your piecewise function is going to do for you. So we're going to have to look at the limit as x approaches 1 from the left of our function. And so from the left, that's all the values of x that are less than 1. So I need to go plug in, and I'm going to have 3 times 1 minus 1, and that's going to give us 2. Now let's look at the limit as x approaches 1 from the right, which is going to be all the values bigger than 1. So I'm going to substitute in here to the 3x squared. So I'm going to have 3 times 1 all squared, and that's going to give me 3. So notice what happens here. The limit from the left is not equaling the limit from the right. So anytime that happens, we're going to say that our limit does not exist, and we've just shown that here. So here my answer would be does not exist, because these two numbers do not equal each other. All right, so let's talk about number 16. Number 16 has some algebra. When we plug in 0 for h, notice that, and we're doing that because that's what h is approaching 0. So we're going to have x squared minus x squared over 0. So that's going to give me 0 over 0, which means we've got some kind of algebra magic here that's got to happen. So we're going to call that algebra magic. And so let's go ahead and pull this out. So I'm going to have x plus h times x plus h minus x squared. I'm going to just address this mess right here. So if I FOIL out the top there, that's going to give me x squared plus xh plus xh plus h squared minus x squared. Again, bringing over the rest of it all over h. And so I end up with x squared plus 2xh plus h squared minus x squared, my gracious, all over h. So again, we've not done the limit yet. We are just simply trying to go through and reduce this down. So our x's will cancel, so I have 2xh plus h squared, and that's all over h. And it looks like the h's will reduce down. So our limit now that we need to evaluate is going to be the limit as h approaches 0 of 2xh plus h squared all over h. Or no, we went ahead and, well, we'll go ahead and carry that through. Now let's cancel those h's, and there's at least one h left there. So that limit is really the same as the limit as x approaches 0, or h approaches 0, sorry guys. H approaches 0 of 2x plus h. So that means this value right here, h is approaching 0, not x. So when h is 0, that means all that I have left is 2x. All right, moving on. All right, now let's talk about limits, or practice them with piecewise functions. So here, whenever we're going through, we have to pay attention to which side we're approaching from. So, and that's going to tell us which part of the piecewise function we need to use. So here we're approaching 2 from the right side. So if I'm approaching from the right side, that means all those x values have got to be greater than 2. So we need to find the function f and find where x is greater than 2, which is going to be this portion right here. And so I need to make that substitution. So I'm going to have 2 squared minus 1. So that's going to give us 3. Now for 18, they want the same idea, but now you're approaching from the left. So that's going to imply all the x values that are less than 2, which is going to be this top portion. And so when I substitute in, I'm going to have 2 plus 3, which is 5. Now, number 19 seems repetitive. However, whenever you're looking at just a limit, you have to look at the limit as x approaches 2 from the left of the function and see if that equals the limit as x approaches 2 from the right side of the function. And so we've done that with 17 and 18. From the left side in 18, we saw we had 5, and from the right side we have 3. Those do not match, so this does not exist. Now for number 20, it's asking for the actual function value. So this is going to be in your inequality. This is going to talk about the or equal to. So that's what that one's talking about, which for this case would be that middle one. And so we are going to plug in 2 squared minus 1. And so the actual function value at 2 is 3. All right. So 21, same idea again. And we are talking about f at x. And we are talking about approaching 4 from the right side. So that's going to be all those x values that are greater than 4. And so we need to find the portion that's going to be greater than 4, which looks like it's going to be the bottom part. So then I'm going to have the square root of 4 plus 5, and that should give us 3. Okay, now from the left, so that means all those x values that are less than 4. And so that's going to be our center part of our piecewise function. And so I'm going to plug in and have 4 squared minus 1, which is going to give us 15. And again, 23 is just like 19. Does the limit as x approaches 4 from the left of our function, does that equal the limit as x approaches 4 from the right of the function? And notice that it doesn't. Once again, we have 3, which cannot be 15, so this does not exist. And then next, it asks for that actual value of f at 4. So this is talking about, again, the or equal to part of your inequality. And so notice that or equal to is going to be the bottom. So we're going to have the square root of 4 plus 5, which is going to give us the square root of 9, or 3. All right, so same pattern again. We're just changing our function from f at x to g at x, but it's still the same idea. So I'm approaching 1 from the left. So that means I need to plug into the top part, and so that's going to be 4 minus 1 squared, which is going to give us 3. And again, we're going to be approaching from the right side, and this one this time doesn't have a function. It's just a constant value of 7, so that's going to be 7. And so we see that that limit does not exist. And then if we need the actual value, g at 1, we need to go see where we are or equal to at 1, and that's going to be the top part of that piecewise function, so that's going to mean that our actual value is 3. All right, moving on to 29. Same idea, same process. We're still just going through our piecewise. So the limit as x approaches 3 from the left, that's going to be our 7. From the right, that means we're going to plug into the bottom, and so I'm going to have 2 minus 3, which is going to be negative 1. And then that tells me that the limit from the left is not equal to the limit from the right, so it does not exist. And then finally, the actual value at 3 is negative 1.